Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. All right, let's do some introductions. Chris, you are Chris Bullheis, high school science teacher extraordinaire in the great state of Michigan. I am Jesse Reimick, geoscience professor at Penn State and your former student. And this is Planet Geo, a podcast where we talk about some amazing aspects of our planet and why they matter.
All right. Hey, Jesse, how we doing today?
Yeah, man, we're doing all right. How about you, Chris?
Right. Doing all right. Hey, so let's go ahead and get this thing rolling. Today's topic is about plate tectonics.
Oh, yeah.
And I wanted to ask you, what's getting you fired up right now?
Yeah, I've been pretty excited about future courses I'm going to teach. A colleague suggested to me that I should offer a class on the early history of the Earth and the early history of our solar system. So that's kind of what I've been thinking about quite a bit this week, and I'm pretty excited about it. What about you? What's got you pumped up this week?
Well, yeah, this week has been a big week with the whole coronavirus thing going on. I take 26 high school seniors out west on a 3-week geology field course. So I'm trying to figure out how to get this to go.
Right.
Yet within this. And I want to, we're trying to figure out how to do this smart and safe. But it's important. I don't want these students, because if they miss this opportunity, then they miss the opportunity. It's gone.
Yeah.
And I don't want this to go by without having them, have the opportunity for that exposure.
Oh, that's great. That's such an amazing experience. Most people from Michigan, have never seen the mountains until that point in time. Right. Anyway, this episode, we're dedicating this to plate tectonics. We're going to talk about what is a tectonic plate.
And I think it's important, though, why are we doing this right away? Plate tectonics lays the foundation for really everything that happens in geology. And so, but before that, there was this idea of continental drift. And that was, about roughly 100 years ago, 1912-ish. So over 100 years ago, this idea that was really groundbreaking of continental drift, the idea that the continents are moving about, came into being from this a guy that I have a lot of respect for, Alfred Wegener.
I mean, the early geoscientists they're just impressive people, just creative thinkers, thinking outside the box.
To me, one of the interesting things about Wegener is that he was not a geologist. He was into, climatology and studying things like this. And so, but one day he was staring at a map. And he looked at the map and recognized right away that if you look at the shape of the east coast of North America and South America, and then you look at the shape of the west coast of Northern Europe and Africa, and you have this classic S shape.
Yeah.
Wegener looked at that and said, wow, they look like they fit together like a jigsaw puzzle. And that's how it kind of all began.
Yeah. It's such a cool, first order observation.
It started with that idea, but then if you put them together, Wegener had a team of people working for him. The evidence that they came up with is just amazing.
Yeah, so let's go through a couple of those. Yeah, hit me with it.
Yeah, so you look at the eastern part of the United States, the Appalachian Mountains. Okay, well, the Appalachian Mountains are the same as the mountains that you see in Northern Europe. They're the same rocks, the same fossils, the same structures. They're the same mountain range. He looked at that and recognized that, those mountains, they formed when Pangea came together. When that supercontinent, you had this continent-to-continent collision, and it formed those mountains. When Pangea broke apart, that's what we see today. And they're separated by thousands of miles of ocean right now.
They broke apart, which formed the Atlantic Ocean, right? So these things just match up. It's a jigsaw puzzle. They match up perfectly.
Everything that they said was correct. The continents were moving. Things were moving.
So it led to this idea of continental drift, which is a nice idea, right? That these plates used to be together and it used to form this one big supercontinent. Okay, looking back, it all fits, beautifully, and we have a way to explain it now. But back then, this was not a well accepted idea, right? There weren't many geoscientists back then, so maybe he pissed off 2 or 3 people in the world, but it was not popular, right? And so
no, this was not accepted.
And the reason was that didn't have a process. There was no really good way to explain why did the continents move around, right?
Yeah, that's exactly what happened. They're like, well, wait a minute. So if the continents moved, how did they move? Bottom line is it came down to the crust plowing through the mantle.
Right.
And it was quickly proved by physicists as being, this is not possible. This didn't happen. And so the whole idea was rejected.
There's also a couple other, potentially a little bit more ridiculous ideas that were used to explain this, like an expanding Earth. The Earth used to be really tiny, and then it just kind of started growing. And if, you can imagine like blowing up a balloon. If you draw some face on a balloon and then you blow like a deflated balloon, then you blow up the balloon, the face gets big and ridiculous, right? The same could be said for Pangea. You blow up the Earth and Pangea breaks apart into all these different continents. Looking back, it's a bit silly. This also led to the perception that continental drift was linked to some of the more ridiculous processes that it was assigned to, and then therefore continental drift was ridiculous, right? Which isn't the case.
No.
So you got to have a good process. You got to have a good hook to explain, what you're observing in the geosciences.
Right, but let's look at that a second, Jess. Like he didn't, 3/4 of the Earth is ocean.
Right.
And Alfred Wegener, we had no idea what the ocean was like. We thought the ocean was deep, which it is. We thought it was flat. We thought it was featureless. And it's anything but that. And so, think about, he came up with everything that he came up with, which was spot on, but without the knowledge of over 3/4 of the Earth, right. Which to me is just absolutely amazing. Here's what Wegener knew. Wegener knew that there was a difference between the crust and the mantle below us.
Which is really a compositional difference. We're sitting on continental crust, there's oceanic crust, and it sits on top of the mantle, which is this sort of, the bulk of the Earth is this mantle.
The crust is the skin of the apple.
Oh, totally. It's where all the action happens, in my opinion. But there's a lot of people out there who kind of love, studying the mantle and all the details about the mantle.
I feel kind of bad for Alfred Wegener. He died in Greenland in, I think, 1930. And he died, I think, unhappy, because this was a lot of his work, and it was soundly rejected.
Yeah.
And it kind of went to bed.
Now, looking back, we understand he was, his observation was spot on, and we have all these new ideas that really led to the main revolution in the geosciences, which was understanding that continents do drift around, and the driving force is plate tectonics, which is the process that governs why the continents are why plates are moving around on Earth. So let's give a brief little, what is a tectonic plate? How do we kind of define that,
Okay. We talked about the crust and the mantle. Wegener knew about this 110 years ago. The compositional difference and the thickness difference, oceanic crust is much, much thinner, but it's denser, and that's a critical thing to plate tectonics. Yep. The continental crust is much thicker, on the order of 70 kilometers thick, but it's less dense, which is a crucial thing in terms of plate tectonics that we'll get into later also. But the lithosphere is the cold and crunchy part of it's the crust and the upper mantle. The lithosphere is about 100 kilometers thick. And here's the way I think of it. It's brittle, it's cold, and it's crunchy. Okay, that's what a plate is.
So when we talk about crust and mantle, we're talking about really a compositional difference. These are, this is the eggshell on top of the egg. But when we're talking about a tectonic plate, we're talking about a really a behavioral difference where the lithosphere, what we're calling lithosphere, this is the crust and the upper part of the mantle, the stuff that is cool enough where it behaves rigidly. This stuff will break. If you bend it, it's going to break, right? That's really kind of what we're talking about with rigidity.
That's such a good point to bring up, because the crust and the mantle, what Wegener knew about, that was a compositional difference that brought that change about. Okay, the lithosphere spans that compositional difference, so we can throw that aside. Right. We can get rid of crust and mantle right now, and we can just say, all right, the part of the Earth that behaves in a cold, crunchy way. That's what a plate is, and that's called a lithospheric
cold and crunchy. I love it. I mean, it's it's something that's it's a little bit cool. If it's like plastic, right? You cool it down, it's going to break really easily. Like, right? If you live in a place where you get a little bit of winter, plastic, it gets cold, it breaks. If you're sitting in North America, you're moving in the same direction as the crust, which you're sitting on, which is like 60, 70 kilometers thick, something like that. Some places 30 kilometers. Okay, there's variability. And then you're sitting on top of another 50 kilometers or so of mantle, which is a different composition, but it is also behaving like this cold plastic. If you bend it, it will break. That is your tectonic plate. And what you're sitting on top of is mantle, same composition, but it's a little bit hotter. So this stuff is like when you heat up plastic, it'll flow. It's not going to, if you bend it, it will not break. If you bend it, it will just kind of flow and deform.
So the asthenosphere, which by the way is my favorite layer of the earth.
I didn't know we had favorite layers.
This sounds like a stupid question. Like, hey, Mr. Bullheist, what's the favorite layer of the earth? Well, you know what?
That's like the most boring answer possible. Like, I mean, come on. Your most favorite layer of the earth is the asthenosphere. Okay, just because what? It's the biggest or something? Come on.
Why is it? Because you know what? The asthenosphere makes plate tectonics happen. And if we didn't have the asthenosphere, we wouldn't have plate tectonics. If we didn't have plate tectonics, we wouldn't have the mountains, and we wouldn't have the valleys and everything in between. So because we have plate tectonics, we have the awesome planet we have, flat out. So the asthenosphere is my favorite layer of the earth. And to me, Jess, you got to give me credit. That makes sense.
I mean, all right, I'll throw you a little bit of a bone. I mean, I like it for the most part. I think there's some more interesting layers of the earth, but important does not equal favorite for me. But I see your point.
Plate tectonics was the unifying theory. It really didn't come about until the 1960s, and it's interesting how war kind of brings on new technology.
Absolutely.
And so during World War II, we had developed, I don't know, prior to World War II, obviously, but it was used widely, though, as sonar. And so during World War II, Harry Hess, he was in command of a ship. As he was, steering his ship from one destination to another, he would turn his sonar down because he was a geologist. He was a curious guy. And so he started making maps of the ocean floor. And we found out that, the abyssal plain, that's what the ocean floor is called. Abyss is deep and plain is flat, right? Well, we found out that it's deep, but the ocean floor is not flat and featureless. Wagner had no idea of that. That led to the discovery of these mid-ocean ridges and so on. And, I talked about earlier when we first began the S shape of the east coast of the U.S. and the S shape of the west coast of the U.S. Well, you know what we found? We found an S-shaped ridge in the middle of the Atlantic Ocean.
Oh, man.
That's crazy.
It's crazy. But it takes generations, right? I mean, it takes technological development. It takes exploration. It takes that kind of stuff. And it takes a long time to really piece together the fundamental ways that the Earth operates. But, like you said, we find these mid-ocean ridges. And then as we started to be able to detect, this magnetism in rocks.
Let's get into that just a little bit. It's the smoking gun of plate tectonics.
Right.
Paleo is ancient, old. Magnetism is the magnetic record in iron-bearing minerals. Okay, well, here's what happens. When lava, which comes out on the ocean floor, in geology we call it mafic, which means it's loaded with iron and magnesium. And so these iron and magnesium-rich minerals, these minerals begin to grow, and they're in this soup of magma. Right? So that means they're free to align, like a compass needle. Mm-hmm. A compass needle, in order for it to work, it has to be free to move, right? Well, because these iron-rich minerals are in this soup, they're free to move. They're in a liquid. They point like compass needles, because every compass has a north and a south pole. They point like compass needles according to where the north and the south poles are at that point, the magnetic north and south pole. But Earth's magnetic field reverses. It flips where our magnetic north pole becomes the magnetic south pole and vice versa. So what do we see when we go to a mid-ocean ridge and drive perpendicular away from it? We see these magnetic reversals. And then when you go back to that mid-ocean ridge and drive the other way, perpendicular to it, right? You see the exact same pattern. They're mirror images on either side of it because the magnetic record is preserved when that lava erupts out and cools below the Curie point.
That's right.
And then gets magnetized and locked in time because now it's cemented in rock, right? But as that's going on, it's getting shoved aside by this plate tectonic movement, this convection below the lithospheric plate. Mm-hmm. And so then if a magnetic reversal happens, now all of the North Poles are pointing the other direction.
I mean, it's such a cool thing because these, the time when the magnetic field flips, it can vary, and et cetera, and the eruption rate can vary at all these different mid-ocean ridges. But what you get is this kind of variable thickness of these little stripes, right? And it creates this basically barcode of Earth history. So that's like, the smoking gun of plate tectonics, which in the 1960s really became the paradigm that governs the geosciences, is that we have these tectonic plates that are moving around on Earth's surface. And the point is that if you're sitting there at home listening to us on your continent, you're sitting on a continent, you're moving right now. You're moving at a very slow rate. I mean, we're talking like centimeters per year. So you can't.
Yeah, it's comparable to the rate that your fingernail grows. That's the common analogy out there.
Super slow, right? You won't notice it. But if you're sitting, somewhere in North America, anywhere in North America, you're, for the most part, moving in the same direction as everybody else in North America at relatively the same rate. But we're moving in a different way than people sitting in Europe or people sitting in Hawaii or people sitting, in Australia. We're moving away from each other and closer to each other. So let's kind of like summarize this. I mean, the take-home points of plate tectonics, a tectonic plate is this cold part, this the crust and the upper part of the mantle beneath us. That's the stuff that if you bend it, it will break. It's behaving like a rigid thing. It's behaving like cold plastic. That's a tectonic plate. And because it's behaving, if you bend it, it will break. If you kind of stress this stuff enough, it's going to break, and it's going to break along the edges. So we have these little blocks, these plates that are moving around. What are they moving on? They're moving above this asthenosphere, which is the plastic part or the hot plastic part, where if you bend it, it will flow. So it's moving, it's kind of sliding around on top of stuff. They're interacting in really interesting ways. In some ways, convection or this sort of plastic flow is driving the plates to move in different directions. In some places, if you get a plate diving down into the mantle, it'll pull other stuff along with it. So you kind of get these different driving forces that are moving the plates around at different points in time. And that's a really complicated question that we don't really understand. It is if you pick any single tectonic plate boundary, the San Andreas Fault, that's a tectonic plate boundary. The subduction zone, that's creating the Andes, that's a tectonic plate boundary. We kind of know, we know that it's there. We know which direction things are moving in. We still don't really have a great understanding of what the processes are that are driving those behaviors. We don't really understand how a tectonic plate can break. You have to break a rock from 0 kilometers from at the surface all the way down to like 200 kilometers deep, and you have to break it all in one spot. We can't model that. No, we don't really understand how that happens. So it's an astonishing thing, right? But it happens all over the place. We can see the repercussions. We can see it actively happening. But that's what a tectonic plate is, right? Is we have, I don't know how many, there's probably I don't know the number, dozens, I'm guessing, 30 or something tectonic plates.
It depends on where
many?
you divide the line. I mean, we have like, 9 or 10 major plates and then several smaller plates. Don't forget about Juan de Fuca. I love Juan de Fuca.
The last little bit that's just hanging out still there. It's about to go down.
It is. But I do want to jump on something real quick, Jess.
Yeah.
Like, I think what you said is true, that this has got to be the next major thing coming out of geology, is a firmer understanding of the interior of the Earth.
Right.
We know a lot, and we really learned a lot in the late 1950s and 1960s with the testing of nuclear bombs. So we were able to strategically place seismographs and we're able to measure, the way that seismic waves are traveling through the Earth, because we knew exactly when, we knew exactly where these detonations were going to take place. So we really honed in on the interior structure of the Earth. But before I retire, there's going to be just this explosion of knowledge coming out about the way that convection happens in the asthenosphere. And I just think it's the next big thing.
So why does this matter? Why are we leading? Why are we talking about this in the second episode?
That's easy for me.
Okay.
This is the easiest question on the planet for me. I had a professor who was so gifted, and he was one of those rare treats you get in college where this guy, he could just flat out teach.
Yeah.
And he began his intro into plate tectonics talking about an earthquake that he had been in Alaska in 1964. And this was it's a famous earthquake, and he was in it. He was studying glaciers. And his description of the violence of what happened and the horror of it all, my reaction was, are you kidding me? Like, that is so cool. I know you were scared, but man, do I want to feel that, right? Like, what kind of power is that? That's what I was thinking.
I mean, it's so cool. Like, what a powerful thing to have a teacher who can hook you in that way, and really define your life in that sense. But I mean, it's also about the subject matter, right? It's also about, this is important, and it, plate tectonics, and why should your everyday person care about what the hell a tectonic plate is? Well, it's because it defines how our Earth operates, right? It defines where volcanoes occur, where earthquakes occur. All these really important phenomena that matter for a lot of people's everyday lives are fundamentally there because plate tectonics operates on Earth. So, I mean, it's a beautiful story. Have you ever been in an earthquake?
Yeah, it was. I'm embarrassed though. I was in an earthquake.
I mean, you should be more embarrassed than you are. I know I'm
embarrassed often, but that's okay. I gave up on pride a long time ago. But I was in a smaller earthquake. I was in California, and it was maybe a 5. To be honest with you, I thought it was the rumbling of a truck passing by, and then I found out later that it was an earthquake. And can you imagine my disappointment? I'm like, what kind of geologist are you? You are pathetic. You are the worst. All right, so. You
just couldn't even experience it in the moment, right? You couldn't be oh wow, that was an earthquake, how cool, right? You were like, some stupid truck driving by.
So my wife, right? And that was relentless shit after that for what kind of geologist I am for not even recognizing.
It's amazing that you can make a living being a geoscientist if you can't even identify an earthquake.
Yeah, it is. It really is. The other thing is that plate tectonics makes sense of everything that I love about this planet.
Yeah.
Because this planet without plate tectonics, what would it look like eventually? Give it time, right? Without tectonics, you have no force that lifts things up. You only have the force that wears things down.
Right.
And so given enough time, this planet would be really flat and featureless, because then you just have weather and erosion and gravity.
Yeah.
And I don't care to live here on that planet.
It'd be a tough life.
Not my thing.
It'd be a tough life if there was no plate tectonics here. That's right.
Yeah.
That's right. That's right.
So let me ask you.
Yeah.
Okay. What does plate tectonics mean to you?
I think for me, you were that teacher who kind of conveyed this sort of really beautiful picture of the value of the earth sciences, and the interesting aspects. But another added part of it was what drives me a lot today in my research is that plate tectonics, it operates today. We can observe it. We can watch these plates move. We can put GPS instruments on them and watch them move at a couple centimeters per year. We really do not understand when plate tectonics began on Earth. So you can have many different what are called tectonic modes or ways that a planet operates in a tectonic sense. And Earth operates with this plate tectonics. There are plates that move around and interact with each other. We don't know when that started. There's people, very, very good, very high quality scientists out there, geoscientists, who will argue that, it only began about, 800 million years ago or so. There are people who would argue that as soon as the Earth was formed, 4.5 something billion years ago, plate tectonics started. The fact of the matter is that we do not understand when plate tectonics began on Earth history. Was Earth a teenager when plate tectonics began? Was it a young adult? I mean, was it an 80-year-old? We don't really know when plate tectonics began on Earth. And plate tectonics governs.
So
yeah.
this is the problem you're trying to solve with your research,
Right.
correct?
It's absolutely probably the driving force, because it matters for the history of our planet. It matters for how we perceive other planets in our solar system and in other solar systems as we begin to discover more and more of them. It also matters for the history of our planet. It matters for recycling of water back into the mantle. It could be the reason why we have oceans on Earth.
All the resources that we have too.
All the resources. It drives gold deposits. Plate tectonics is fundamental, and it is why the Earth looks the way it is, and why Earth is unique, and why actually there's life on Earth. So I think a good exercise that we should go through here is why, what would Earth look like without plate tectonics? And I think we have some pretty good examples of that when we look around the solar system.
I teach astronomy, high school astronomy, and the biggest known volcano in the solar system is not on Earth. And you'd think, well, that doesn't make sense. We have this active tectonic, planet. Why would Earth not have
That's
the largest volcano?
Plate tectonics creates mountains on Earth. So you would expect
it does. That's what it does.
It would create. Yeah. It wouldn't create mountains if you didn't have plate tectonics, right? But that's not the case.
Right. But Mars has an enormous, Mars has several volcanoes that dwarf anything on Earth. But the biggest one that we know of is called Olympus Mons. It's 22 kilometers tall. Now, this dwarfs anything on an Earth scale.
That's from the bottom of the mountain to the top of the mountain.
Yeah, it's 22 kilometers, which is 13.6 miles tall.
It's amazing.
Now, for scale, Mount Everest is just under 6 miles above sea level to the top of it.
Yeah.
Okay, now that's not necessarily the height of the mountain itself, but that's the tallest point on Earth, right? 6 miles. This volcano is 13.6 miles tall. Now you think, all right, well, why? Mars doesn't have plate tectonics, which means the lithospheric plates don't move on Mars.
There's just one plate.
And so if they have a hot spot, which we'll talk about later on, but this source of magma coming up, right? Imagine this, right? You have this source of magma coming up, but the plates don't move. So what you get then is just this center of volcanism, but the plate never moves. So the volcano just gets bigger and bigger and bigger and bigger over time, right?
That's right.
On Earth, that doesn't happen. You think of Hawaii. Hawaii's a hot spot. Almost everybody knows Hawaii's a hot spot. Mm-hmm. But as that source of magma comes up, and you get these eruptive centers, like for right now, the eruptive center is on the big island of Hawaii, Kilauea, the most active volcano on the planet. But the plate continues to move over top of this hotspot, of this source of magma. And so the volcanoes get to a certain height, and then they have moved past the hotspot, and then a new eruptive center shows up.
Right. It's really one of the coolest things. Google Earth is so cool, right? To just play around with. If you're listening to this and you're having trouble picturing this, go to Google Earth, look at Hawaii, and look at the Hawaii Emperor Seamount chain. Oh. And this is what we're talking about. It's basically a single point eruption that creates this chain of islands, which are now under, we used to be islands, which are now have been eroded down to just below sea level. But it's this volcanic eruption that, because the plate has been moving over it, all that magma has been carried away. All that lava has been carried away from the source. And so on Mars, we don't get that. On Mars, all that magma is just piled up on top of each other. So it creates this Olympus Mons volcano, which is massive. It's just a giant. So the only reason that Hawaii is not, 5 times the size of Everest, or whatever it is, 3 times the size of Everest, is because of plate tectonics. It's so cool. What a cool comparison. It's amazing, right?
Yeah. So I want to say this, that, in geology, we can simplify things down to, we can make it really simple, right? There are 2 forces in geology: forces that lift things up and forces that wear things down. The force that lifts things up is called plate tectonics. The force that wears things down is called weathering and erosion. Plate tectonics makes this planet awesome.
Yeah.
Flat out. There's no There's no denying it.
So,
Yes?
I mean, we were talking about hotspots, and this is a really nice lead into what we're going to talk about next, which is one of our, I would say, well, one of mine, certainly, and I think one of yours, favorite hotspot locations to go visit, which is Yellowstone National Park. So that's all for this week. As usual, thank you for joining us, and stay tuned for our next episode coming up in 2 weeks, where we'll talk about Yellowstone National Park. Again, we are really excited about this project, and as always, we're looking for your feedback and input. So please leave us any questions, topic ideas, or comments on any of our social medias. We are at Planet Geocast, and our email account is planetgeocast@gmail.com. Again, we'd love it if you'd like to subscribe to this podcast, and we'll chat with you soon.